This animation shows three particles, M, N, and D, and the net force acting on each one. F1 is the net force acting on M, F2 is the net force acting on N, and F3 is the net force acting on D. Let M be the mass of this system composed of M, N, and D. Cm is the center of mass of this system. Now let's start the animation. We observe that the center of mass moves like a particle of mass m acted upon by the net external forces acting on this system, because the net force acting on Cm equals F1 plus F2 plus F3. Now let's determine the relation among the acceleration of the center of mass of a system, the net external force acting on this system, and the total mass m of the system. We have seen in the previous episode that the position vector of the center of mass of a system is given by this relation. M is the total mass of the system, so RCM can be written by this new equation. Let's differentiate both sides with respect to time. The derivative of RCM equals VCM, where VCM is the velocity of the center of mass. 1 over m is a constant. The derivative of m1r1 equals m1v1, where v1 is the velocity of the first particle. Similarly, the derivative of m2r2 equals m2v2, and the derivative of mnrn equals mnvn. We can write m times vcm equals m1v1 plus m2v2 and finally plus mnvn. Let's differentiate both sides with respect to time. The derivative of VCM with respect to time equals ACM, where ACM is the acceleration of the center of mass. The derivative of m1v1 equals m1a1, where a1 is the acceleration of the first particle. Similarly, the derivative of m2v2 equals m2a2, and the derivative of mnvn equals mnan. But m1a1 equals F1, which is the net external force acting on the first particle, and m2a2 equals F2, which is the net external force acting on the second particle, and mnan equals Fn, which is the net external force acting on the antiparticle. But F1 plus F2 and finally plus Fn equal the net external force acting on the system plus the net internal force acting on the system. We know that the net internal force acting on the system equals 0. Therefore, the net external force acting on the system equals the total mass of the system times the acceleration of the center of mass of the system, which is called Newton's second law for a system of particles.
Newton's second law for a system of particles is known as the center of mass theorem. The center of mass of a system of particles having a mass m moves like a particle of mass m acted upon by the net external force on this system. Look at the equation. If the net force is not changed, then the acceleration of the center of mass stays the same, even if the motions of the other particles of the system changed. As an example, let's consider a firecracker launched vertically upward in air and moving under the action of its weight only. Observe. When the firecracker explodes under the action of the internal forces, the fragments are ejected in different directions. However, the center of mass of the firecracker continues on its vertical path since no change occurs in the net force acting on the system.
Now, let's take another example about the motion of the center of mass. Consider a skater jumping in air and moving under the action of his weight. The skater's hands and legs move in different directions. However, in air, the center of mass of the skater continues on the same curved path since no change occurs in the net force acting on him.
Focus, please. This is important.
What if the center of mass is under zero net force? Look at the center of mass theorem. M is different from zero. Then, If the net force is 0, the acceleration of the center of mass is 0. Therefore, the velocity of the center of mass is constant. Here we have two cases. The first case, if the center of mass was initially at rest, it remains at rest. The second case, if the center of mass was initially in motion, it continues in uniform rectilinear motion in the same original direction.
Let's take some examples about the motion of the center of mass. In the adjacent figure, two blocks having masses m1 and m2 compresses a light spring by means of a light string. The system is at rest on a frictionless horizontal table. Suddenly, the string gets cut and the blocks are ejected in opposite directions. What happens to the center of mass when the string gets cut? Consider the system: two blocks, spring, and the string. The external forces acting on this system are the weight of the system, m1g plus m2g, and the normal force, n1 plus n2. Applying the center of mass theorem, the net external force equals the total mass of the system times the acceleration of the center of mass of the system. But the net external force acting on this system equals m1g plus m2g plus n1 plus n2. But m1g plus n1 equals 0 and m2g plus n2 equals 0. Therefore, the net external force acting on this system equals 0. But m cannot be 0. Therefore, the acceleration of the center of mass equals 0.
The center of mass was initially at rest, then it remains at rest. The velocity of the center of mass is 0. As you see, when the string gets cut, even though the two blocks are ejected in two opposite directions, the center of mass remains at rest.
Now, let's take another example. In the adjacent figure, a man stands on the left edge A of a long thin boat. The edge B of the boat is against the shore of the lake. Neglect air resistance and the friction between the boat and the water. The system is initially at rest. The man moves from A to B. During the motion of the man towards the shore, the boat moves away from the shore. The question: describe the motion of the center of mass of the system man-boat during the motion of the man and the boat. The external forces acting on this system are the weight of the system and the upthrust force acting on the system. Since the net external force acting on this system is 0 and the center of mass is initially at rest, therefore it remains at rest, so its velocity equals 0.
Let's move to another example. Consider two objects, 1 and 2, colliding with each other while moving on a horizontal frictionless table. The external forces acting on the two objects are the weight and the normal force. The net force acting on this system is 0. The center of mass was initially in motion, then it continues in uniform rectilinear motion in the same original direction. The velocity of the center of mass is constant. Observe.